All right, so we looked at acetic acid, abbreviated HAC. We calculate an average of 1.895. Did we do the standard deviation for this? Not yet? Okay. The next thing is we're going to calculate the standard deviation. The standard deviation is going to give us an idea of the spread. We can get an idea of the spread by looking at the values here. If we look at it, the low value is 172, the high value is 2. And so the spread is about 0.28 right here. Okay, we can do a statistical analysis for this by taking the standard. In Excel, it's called the standard STDEV. Excel has different standard deviations that we can choose from. So I'm going to hit equals and then take a look at what standard deviations we can have Excel calculate. The first standard deviation is P. Calculates the standard deviation based on the entire population given as arguments. Or we have standard deviation S. Estimates standard deviation based on a sample. Or we have standard deviation A, standard deviation PA. And what we're going to do is we're going to use standard deviation S. It estimates the standard deviation based on a sample. Standard deviation, when you look at the statistics, they usually take an infinite number of measurements, and then we can get the standard deviation. Instead, what we're calculating something that's related to it, but it's going to be slightly different because we don't have an infinite data set. We have a limited data set. And so we're calculating standard deviation S variance. And then I'm just going to plug in the data here. These are the values we got. And then I'll have Excel calculate it for me. All right, so the way we read this is like this. I'm allowed 3 sig figs here. So if I were to round my average down, it'd round to 190. And then I'd have the standard deviation to the same number of decimal places. So it'd be 0.10. And so what this says is that 190 plus or minus 0.1 is within one standard deviation. Being within one standard deviation of the average in statistics means we have about a 67% probability that the true value lies within that range. That's the way we think about it. But we don't want 60. If it's something like 67% probability that it lies inside, that means there's a 33% probability that it lies outside, and that's too big. 33% chance that it's outside that range is not good. So what we do is we take about 2 times the standard deviation. In other words, we take the average and then 2 standard deviations out. And if we go to about 2 standard deviations out, then we can capture about 95% of it. It's a little less than 2 standard deviations. And so we have different names. The standard deviation we call the 67% confidence interval because that means there's a 67% probability that the true value is within that range. What we're going to do is we're going to take the 95%. The 95%, if I want to capture 95% probability, then I'm going to have to go like 1.95 standard deviations or roughly something like that. And so rather than saying 2 standard deviations, which would be more than 95%, 2 standard deviations would be like 97, 98%. But the standard in science is to have 95%. So we'll go with that. And we're not going to call it a standard deviation. We're going to call it a confidence interval. And so one standard deviation is a 67% confidence interval. 95% confidence interval would be about 1.95 standard deviations, roughly. So what I'm going to do is I'm just going to have Excel calculate it. And it's called confidence is the formula. And we have two different confidence. Actually, we have three different confidence that we can calculate. I don't know if you can read that, but the first one's confidence.norm. Returns a confidence interval for a population mean using a normal distribution. The next one is confidence.t. Returns the confidence interval for a population mean using a student's t distribution. And then we have confidence, which is no longer used here. So we only have two. We're going to use the student's t distribution. We're going to use the student's t distribution not because you're students. It's because this mathematician's name was student, I think. And so professionals use this as well. In fact, everybody uses the student's t distribution, whether you're a student or not. And so we're going to use this. Now, what do we need to do this? We need alpha. The alpha is, the alpha is the decimal form of what percentage you want outside. And so let's say we want 95%. Then it's going to be 1 minus alpha. 1 minus alpha, well, it's going to be 1 minus 0.05. And so if we type in 0.05 here, that's our alpha, meaning that that would be 5% outside. 95% inside. And then we need our standard deviation. So our standard deviation, we just calculated, that's in cell B79 here. So I'll just click B79. And then we need the size, the sample size. And so the sample size is 6. And then hit enter. And then I'm going to go 2 decimal places for this as well. Let me go 3 decimal places and compare. Do you see the 95% is a little wider? It's 0.105 versus 0.100. But our precision's pretty good, I suspect. And so or maybe our precision is not so great, and so that's why there's not much of a difference here. Usually you expect the 95 to be significantly bigger, but when I do this, they come out the same. So anyway, the more data, the better, and the tighter the precision. Let's say one of these was way off. I'm going to make this, instead of 2.00, let's make this 3.00. If that's 3.00, take a look at what happened to my 95% confidence interval. Now it went up to 0.5 or 0.49. Do you see that? That means we have a lot less confidence because we have this one data point that's way out there at 3.00. Let me bring it back to what it was. It was 2.00. When we go back down to 2.00, then it's good. So the 95% confidence interval depends on how precise your run-to-run precision is. I mean, we see here. And it also depends on how many data points we take. So let me eliminate some of these. Let's go to 2 data points. You know, if we take 2 data points, then we can't have as much confidence in this. And so I'm going to delete these here. So if I take 2 data points, I need to change my sample size. I went from a sample size of 6 to a sample size of 2. So if I go to a sample size of 2, take a look at my 95% confidence interval now. So I can be, I have 95% confidence it lies within an average of 1.82 plus or minus 1.21. That's a huge window, right? And that's because the precision really hasn't changed much. It's because of the sample size. You know, the fewer the samples, the less confidence, because we don't know. The more samples we take, the better. In fact, if we wanted to eliminate random error, we could, if we could take an infinite number of samples, but since we can't quite eliminate it, but we can try to minimize it by taking more samples. When we look at the mathematics of this, in science, the cost benefit is 3 usually. You know, if we go less than 3, like 2, that wreaks havoc on your 95%. It makes it gigantic. But if we just do one more measurement to 3, then it narrows it quite a lot. And so most people go to 3. But the more you do, the narrower the 95% confidence interval gets. It just is nonlinear, so that 2 to 3 is a huge decrease in the width of that. And then 3 to 4 is a small. 4 to 5 smaller, and it keeps getting smaller and smaller, the incremental improvement in your 95% confidence interval. So if we took 1,000 versus 1,001, 1,001 is not really going to help you statistically much, versus 1,000. But the biggest jump is going to be between 2 and 3 for sure. And so most people will take 3 because it takes time to take more measurements. So let's look at the average here for the sodium acetate at 773. And then what we're going to do is I'm just going to copy and paste that. And so here we can see a difference in the 67% versus the 95%. So to capture 67% probability, it's going to just be plus or minus 0.39. But if we want 95%, probability is going to be in that range, then we are going to have to extend it out to 0.41. Does that make sense? Okay. So we did a couple of calculations here. Let's see. We did the calculation. Did we do the calculation for this? We did a calculation where we tried to determine the Ka value based on the experimental data. And we got a Ka value of 5.4 times 10 to the minus 5. However, it's off a little bit because the accepted value is 1.8 times 10 to the minus 5. And it could be off due to different reasons. For example, the acetic acid solution was made to 3 molar. 3 molar is only 1 sig fig. And so that means that could be made anywhere from 2.5 to 3.4, and it'd still give you 3 molar. And so maybe it's a little more concentrated than what we expect. There are other reasons too. All right. The second calculation will be determine the equilibrium concentrations. Here, let me just say that when you have a very small percent change, like a percent change that's much less than 1, then it makes very little difference. For example, if we solve this using the quadratic equation instead, then we pretty much get the same answer. If we add like 10 sig figs, then yeah, it's going to be different. Maybe 6 sig figs is going to be different, but we're only going to have about 2 sig figs, so it's not going to make much difference in the calculation. If this gets closer to 5, though, then I'd rather use the quadratic. If it's not hard, like here, the quadratic's easy. And so if this were 3.5%, then even though we're still below 5%, I might consider using the quadratic because the quadratic is going to give us a better answer. But if you're pressed for time, then you can just go ahead and use the simplifying assumption. 3.5%, still less than 5%, but it's starting to get bigger, and your error is starting to get more significant. So is this where we left off last time? Okay, then we double check the K. When we double check the K, even with the simplifying assumption, we're way off. And I think that's where I stopped, huh? Is that where I stopped? So there's some calculation error because my K shouldn't be that far off. I mean, it should be, we use the Ka value 1.8 times 10 to the minus 5, and I'm at 3.8 times 10 to the minus 5. That's more than rounding. Rounding might be 1.7, something, or 1.8 something, but this is too far off, 3.8. And so I must have made an error. And so let me see where that error is. So we'll just double check. So this is the utility of the double check. here to see if I made some kind of calculation error and then see if I can find out what that calculation error is. So let me double check X again. So X, I'm going to do 3 times 1.8 times 10 to the minus 5. Let's try that. 3 times 1.8 times 10 to the minus 5. And then take the square root of that. Oh, there's my error here. You know, I have trouble punching this on my calculator. So it looks like my X was off. Can somebody double check the X? So basically, what I see, oops. I see this is way off. This is looking like a calc error. And so I went back and double checked this, and then I recalculated my X value here. And I get an X value 0.007348. Normally I carry extra digits to minimize rounding error, you know, because the double check, if you do round overzealously, then you're always going to be way off on your K. And it's hard to see if that's a calc error or a rounding error. So I carry extra digits to eliminate the possibility of rounding error. Therefore, it's got to be calc error. So I'm going to redo these numbers here. Both of these are going to be 0.007348 molar, and this is going to equal the same. And then I'm going to recalculate this. This is minus 0.007348. Which comes out to 2.99265. 2.99265. That should be enough. Enough digits. Okay, so now I'm going to recheck my K. So I'll do 0.007348 squared and then invert that multiply. So I'm going to invert what I have in my calculator times 0.007348 squared equals. Okay, now this is way better. This comes out to 1.80418 times 10 to the minus 5. So that checks out. Okay. I need to make sure I didn't justify. This is a smaller change, so the percent change should be even better. And so the percent change comes out to 0.007348 divided by 3 times 100. 0.244. Percent. And so even better. With a percentage like 0.244, then if I did the quadratic, it wouldn't make much difference. In fact, we could show this by doing the quadratic. This one, the quadratic's not too hard to solve. So let's do that over here. So I'm going to use the quadratic instead of the simplifying assumption. So I'm going to get 1.8 times 10 to the minus 5 is equal to x squared over 3 minus x. And so I'm going to get x squared plus 1.8 times 10 to the minus 5x minus 3 times 1.8, 5.4 times 10 to the minus 5 is equal to 0. And then I'm going to use the quadratic solver for this. So you could either have your calculator, or if you're doing homework, you could just have this set up on a web page here. That was 1, B was 1.8 e to the negative 5, and then C was 5.4, or negative 5.4 e to the negative 5. 0.00739. 0.00739. Well, it came out a little different. 0.00739. But according to the number of sig figs and the number of decimal places were allowed, maybe we'll get a little bit better K value. But it didn't make much difference. A little different. And so if we can get this percent change even lower, then it would be better. Anyway, going back to this, acetic acid is a weak acid. And in this case, it is 0.24% ionized. Because the reaction is an ionization or hydrolysis reaction. So it's 0.24% ionized or 0.24% hydrolyzed. So it's a weak acid. Now, can we say that acetic acid is always 0.24% ionized? And the problem is we can't say that, because the percent ionization is kind of weird. So let me talk about percent ionization for a little bit here. This is percent ionization / hydrolysis / reaction. Pretty much all the same for acids. For bases don't ionize, bases hydrolyze. Versus the concentration of the acid, HA. And what we see is that the percent ionization changes with concentration. And in fact, it forms a curve like this. So it depends on your initial concentration here. The higher the initial concentration, the lower the percent ionization. So the more concentrated the solution is, the less ionization we get. The lower the concentration, the higher the percent ionization. So as we go to infinite dilution, we go to infinite ionization. This is for a weak acid. And so at one concentration, it could be about 0.25% ionized. At another concentration, it isn't necessarily 0.25% ionized. However, strong acids behave differently. Strong acids are about 100% ionized, just slightly less. If it were 100% ionized, then Ka would have to be infinity. And there are no Kas that are infinity, so it's slightly less than 100%. But the behavior is quite a bit different because we can say that strong acids are completely ionized or close to it, where weak acids are partially ionized, and the degree of ionization depends on the concentration. So we're not going to characterize it based on the degree of ionization. So HA will have variable ionization depending on the concentration, but they're all kind of small, unless we get to infinite dilution. But if we're looking at infinite dilution, then the solution doesn't have much practical use. All right, any questions on acetic acid? Okay, the next thing we're going to do is we're going to do sodium acetate. And sodium acetate is a base. Since sodium acetate's a base, we have Kb. In other words, base hydrolysis. Base hydrolysis is going to look like this. So we take our acetate, actually, let me do it this way. That's a lot to write. And so we're going to call acetate AC minus. It's abbreviation for acetate. Plus water yields what? So what are we going to form in this case? Acids hydrolyze water to produce hydronium and the conjugate base. Bases hydrolyze water to produce what and what? Well, one is the conjugate acid. What's the conjugate acid of acetate? Acetic acid. Acetic acid, I'm going to abbreviate HAC. Plus what? Hydroxide. So bases hydrolyze water to produce hydroxide. Acids hydrolyze water to produce hydronium. We'll get a Kb equation for this. This is base hydrolysis. Kb, did I already do Kb? I don't think so. But Kb is going to equal the acetic acid concentration at equilibrium times the hydroxide concentration at equilibrium divided by the acetate concentration at equilibrium. Did you guys use the pOH meter? Did we forget to take the pOH readings? The reason I'm asking is because we don't have any hydronium here. We have hydroxide, so I need to know the pOH, the power of the hydroxide concentration, not the pH. Because it's a base. Bases, we should be dealing with hydroxide, not hydronium. So we probably should redo the measurements using a pOH meter, not a pH meter, correct? It turns out, no. If you try to go out and buy a pOH meter, they don't sell them. Why don't they sell the pOH meters? They only have pH meters.
Because you can get the pOH from the pH?
Yeah, right. Yeah. We don't need it because we can get the pOH from the pH, exactly. And so how do we get that? Well, if you recall, Kw was equal to the hydronium ion concentration at equilibrium times the hydroxide ion concentration at equilibrium. So if we know the hydronium ion concentration at equilibrium, which we can get using the pH, we know what Kw is. Kw is 1.0 times 10 to the minus 14 at 25 degrees C. We can solve for the hydroxide concentration. Or we could use this equation. We could take the negative log of the entire thing. If we take the negative log of the entire thing, then what we're going to do is we're going to get the negative log of Kw is equal to the negative log of the hydronium. I'm using the properties of logs. Log of a product is the sum of the logs, so it's going to be plus a negative log of the hydroxide. I don't know what this thing is here. Well, actually, the negative log of, did I talk about power function before? So for example, the power function of x is just equal to the negative log base 10 of x. It goes by powers of 10, so that's why it's logarithmic here. And so here, the negative log of Kw is what we call pKw. It's the power of Kw. Do you guys recall what Kw is? Kw is a number most people memorize, too. 2 sig figs. Kw is equal to 1.0 times 10 to the minus 14. And so the power is 14. But we should have 2 sig figs right on 14. Let me pause this. Okay, let's resume here. So we have this relationship Kw. Did I derive this last time? The relationship Kw. Yes? Okay. And then this is equal to pKw, and then negative log of the hydronium is the pH, and then negative log of the hydroxide is pOH. And so pKw is 14.00, and so the pH plus the pOH have to add up to 14.00. So if I know what the pH is, then I can convert that into pOH, and once I have the pOH, I can convert that into the hydroxide ion concentration at equilibrium. So from the pH, I'll calculate the pOH and then get the hydroxide ion concentration at equilibrium. And then I'll have that for my ice table here. And so the acetate, what was the initial concentration of the acetate? The acetate, I think, was 0.1 molar. Waters appear liquid, and so we can omit that from the ice table here. And then the hydroxide ion concentration we can get. And so the average pH for sodium acetate came out to 773. And so let's go ahead and calculate the hydroxide ion concentration here. It's going to be 10 to the minus pOH molar. And so this is going to be 10 to the minus 7.73. Do you know what pH neutral is? 7.00. And so this is just slightly what we call basic. pH is higher than 7 or basic, pH is lower than 7 or acidic. And so since this is close to 7, it's just slightly basic. All right, we can punch that into the calculator and then see what we get for the hydroxide ion concentration. And I got a hydroxide ion concentration 1.862. I carry extra digits, again, just to minimize round off error, but I got to get rid of them. Times 10 to the minus 10. Is that what you guys got? Maybe I'm off. 3, 6, yeah, I'm off. It should be between negatives, yeah. So let me fix that. 3, 6, 7, 8. Yeah, times 10 to the minus 8. That's kind of what we expect. It should be around 10 to the negative 8, 10 to the negative 7, 10 to the negative 9, in that range. All right. So then what we're going to do is we're going to plug these concentrations in to the table here. So this was initially 0 and 0. We assume nothing's happened. And then we're going to go minus X molar, plus X molar, plus X molar. And so this will be 0.1 minus X, X, and X. And so that was 1.862 times 10 to the minus 8. And the hydroxide will be the same. For every acetic acid we make one hydroxide. And then this is going to be 0.1 minus 0.9, I need 7 zeros. 1, 2, 3, 4, 5, 6, 7, 1, 8, 6, 2. Which is going to give me 0.099, how many nines? 2, 4, 6 nines. And then an 8, 1. So what we do next is we double check the K value. Double check the calculation by checking the K value. So double check K, which is going to equal 1.862 times 10 to the minus 8 squared divided by 0.099999981. I got a K of 1.8 times 10 to the negative 7, 1.86. Is that what you got? What did you get?
4, 6, 7, times 10 to the negative 15.
Times 10 to the negative 15. Anybody else? You got that? Times 10 to the negative 15. Okay. I must, since you two got that, 3.467 times 10 to the negative 15, let's go with that. Yeah, mine's way off. Way off. Okay, that looks good. Now let's compare that to the accepted. That's our experimental K value. All right, we'll have to hold for a moment here. Try to get this working again. Oh, it's not going to work. What was it again, Tristan? $3.467 times 10 minus 15. All right, let's look at the accepted value. We're looking up the Kb for acetate. I'll just abbreviate AC minus. This isn't going to record, so but the morning I recorded it, so just take a look at the AM. The problem is there's no Kb value listed. We go to Appendix B or D. Appendix D has more data. It's still not there. And so, should I continue looking for it in a KB table? And so, this comes down to the same question I had asked earlier, and that is, should we buy a pOH meter or can we survive with a pH meter? We can survive with a pH meter, but the pH meter measures hydronium, and we have a base here. But there's a relationship between conjugate pairs. And that is, when I was doing the Kw, I came up with this equation here, and that is the Ka for a generic acid, HA, times the Kb for the conjugate base, A minus, is equal to Kw. The restriction is these have to be conjugates. And that's the reason why, like, we can get by with just the acid table. If we have the acid table, then the stronger the acid, the weaker its conjugate base. So we automatically have a ranking for the conjugate base. We can get by with the oxidizing agent table. You know fluorine, then the conjugate reducer is fluoride, and fluorine's very powerful, and fluoride's very weak. And so we still have this up and down ratio. So if Ka is large, which means it's strong acid, the stronger acid is greater percent reaction, percent ionization, percent hydrolysis, then that means its conjugate base must be weaker, and therefore Kb is smaller. So if Ka is big, Kb is small. If Ka is small, Kb is big. And so it's this seesaw relationship between conjugate pairs. The same thing. If the oxidizer is strong, its conjugate reducer will be weak. And so we don't need both tables. We either need a Ka table or a Kb table. It doesn't matter. We need one. And so if I needed the Kb for acetate, acetate's not on the table, but its conjugate acid is. What is its conjugate acid? Acetic acid. So all I have to do is I go Kw over the Ka for acetic acid, HAC. This is not acetic. This is just a general anion, generic anion. Kw we usually memorize at 25 degrees C. At 25 degrees C, it's 1.0 times 10 to the negative 14. Kw grows bigger at higher temperature. At higher temperature, you have more violent collisions, and you'll generate more hydronium and hydroxide. But at 25, it's this. And now Ka for acetic acid, we looked up earlier, was 1.8 times 10 to the minus 5. And so this is going to give us a Kb for acetate equal to 5.55 times 10 to the minus 10. And so this is the accepted value. Our experimental value is 3.467 times 10 to the minus 15, which was way off. It could be way off because, the concentration might be way off, or it could be way off because calibration's off. There's some kind of systematic error, etc. All right, so what we're going to do is what pH should we have measured for this? And so we're going to do another calculation with this. We want to figure out what the pH should have been. We measured what we got experimentally, but in theory, what should the pH have been? Given our initial concentration of 0.1 molar acetate and our accepted Kb value, the accepted Kb value for acetate is 5.55. We're only allowed 266 times 10 minus 10. So why don't you go ahead and try to calculate the pH for this? Let me see. Did somebody get it? No. All right, the first thing is we need the KB. KB is going to be base hydrolysis. So we take our base with water. What do we form? Acetic acid and hydroxide. So bases hydrolyze water to make hydroxide. Acids hydrolyze water to make hydronium. So we know that the acetate's 0.1 molar, water is a pure liquid. We're going to assume nothing's happened yet. And so both of those are 0 molar and 0 molar. There's going to be a change. This is going to be minus X molar, plus X molar, plus X molar. So that at the equilibrium, we're going to have 0.1 minus X molar, and then X molar, and then X molar. When we have Kb over there, that Kb is going to equal the acetic acid concentration, which is X, times the hydroxide concentration, which is X. So that's going to be X squared over 0.1 minus X. And this whole thing is going to equal 5.55 times 10 to the minus 10. Now you look at it, 10 to the minus 10 is heavily favored towards reactant or product. Ten to the minus 10 is heavily favored. This is, proportional to the products of reactant. And so which side is going to be bigger? The top side or the bottom? Favored. Which side is favored? Well, 10 to the minus 10 is like this. It's like a 1 over 10 to the positive 10 ratio. And 10 to the positive 10 is 10 billion. So this is like a 1 to 10 billion ratio. which means that you're going to have 1 part of product to 10 billion parts of reactant, which means the reactant side's favored. Now, it's not going to be exactly like that because the numerator is squared, the denominator is not squared, so it's not linear like that. But just roughly speaking, we expect, excuse me, if I had a billion, 10 billion, only one of them will go across to the other side. Is that very significant? Is that a big change? Small change. That's a small change. If it's a small change, then the SA should work. Did I talk about the ratio? You know, Petrucci asked you to calculate a ratio. It's going to be the ratio of the initial concentration, which is 0.1. So we're starting off with this initial population. And then we divide by the K. The K is 10 to the minus 10. So this is 10 to the minus 1 divided by 10 to the minus 10, which is going to give us 10 to the positive 9 to 1. If this is greater than, let's say, 1,000, then the SA should work. And the bigger it is over 1,000, the better. I don't bother calculating the ratio. I just go ahead and try it. If it doesn't work, that's fine, because it takes so little time. So if we use the SA here, we're going to say x is much smaller than 0.1. And then this is going to simplify into x squared over 0.1. And so let's go ahead and calculate x. .55 times 10 to the minus 10 times 0.1. And then square root that. One, two, three, four, five. So I get an x that equal to 7.449 times 10 to the minus 6 molar. This is going to be the same, 7.449 times 10 to the minus 6 molar. And this is going to be 0.099925 molar. Okay, I'm going to invert this times 7.449 times 10 to the negative 6. I screwed up the calculation. So a couple of things I need to check. One, I need to check the percent change. I need the percent reaction, percent hydrolysis, percent ionization. That's going to equal the change over the initial. This is going to equal x over 0.1 times 100%. X is this 0.123450 is 0.123457449 divided by 0.1. Actually, I didn't need to do this in my calculator. This is 10 to the minus 1, that's 10 squared. And so this is going to come out to 0.007449%. This is a very small change. So SA should work well. And so if we did this using the quadratic formula, we'd probably get very close to the same answer. All right, ultimately, we want to double check our K. So we'll double check K. by going x squared over 0.1 minus x. Point 7.449 is 10 to the minus 6 squared divided by 0.0999925. I have 5.549 and 10 to the minus 10 is pretty close to 5.55 times 10 to the minus 10. So we're good. So that's a base.
Sorry. To get from the concentration of OH to pOH,
I'm sorry?
concentrate from the concentration of OH to pOH,
Yeah.
it's 10 to the basically 10 to x.
Right. So you want to go from here to pOH.
Yeah. To get so the question is to get pH right, and then
No, this one we already had the pH. Oh no, you're right. Oh, we're not quite done yet. Not quite done because we need to go to the pOH. So the power function is this: pOH is equal to the negative log of the hydroxide ion concentration, and then the hydroxide ion concentration we take the anti-log both sides. Take the anti-log, that's actually the negative. And so that comes out to the negative pOH molar. And so we want the pOH, so we'll just plug in the concentration here, take the log of that, and change the sign. And tell me what you get for the pOH. Okay. That's the pOH, but I didn't ask for the pOH, I asked for the pH. The pOH and the pH have to add up to 14. And therefore the pH is equal to 14.00 minus the pOH. And so this is going to give you 4.645. Is that what you guys get? Seven?
no 4.7.
4.7 for the pH. There's something wrong here. Unfortunately, there's something wrong.
I got a 5.127, 128 for the pOH.
For the pH, you got 5.127.
127.
And then your pH comes out to
8.87.
all right. The reason why I said something wrong is because 4.745 is what we call acidic. But this is not an acid. Acetate's not an acid. Acetate is a base. And so it couldn't be 4.745 is wrong. It can't be 4.745 because it would make it an acid. This is a base, 8.87. But we didn't get it. We got 7.3 something, right? As our average. So our pH readings were a little bit low. Maybe it wasn't concentrated enough. Do you know what you should know what the pHs range from? What to what? What do pHs range from? Typically? People say pHs range from 0 to 14. And right in the center, we have pH 7. pH 7 is what we call neutral. So pure water is neutral. There are other solutions that are neutral as well. If we have a pH around the 14 range, that's strong base. Strongly basic. If we have a pH around 0, we call that strongly acidic. Things here are moderate. This would be moderately acidic. And between 7 and 14, somewhere in there, we'll call it moderately basic. How about a pH of 14 plus? What should we call that? Could we have a pH higher than 14? Is that possible? Or does pH stop at 14? We could. This is very strongly basic. Could we have pHs that are negative? Yes, we can. These are very strongly acidic. But we try to narrow the range between 0 and 14, and there's a reason for it. The reason for it are all these equations. So, for example, the pH is equal to the negative log of the hydronium ion concentration. Uh-huh.
What if you drink something that's like a pH of 15?
Probably be pretty painful.
Really?
Yeah.
But why is it the higher the pH in the water, the better?
Not the higher. They only go up to like pH 8, maybe. You're talking about alkaline water?
Yeah.
Yeah, you don't want to go too high. And so a little bit high is okay. A little bit high, when you drink it, it tastes it has a different taste to it, and it goes down quite smoothly. Have you ever spilled sodium hydroxide on your fingers? If you spill sodium hydroxide on your fingers, it becomes very slippery. Yeah.
Because our bases like
Bases are like soap.
yeah.
And so, if you're drinking something like pH 14, around there, you're drinking like heavy detergent.
So would thick water have a stronger pH? Or stronger pH?
Thick, you mean more viscous?
Yeah.
Yeah. As the pH goes down, it becomes less slippery. Yes, you could say. And so some people like that, but anyway, you don't necessarily want too high of a pH because too high of a pH will start to cause damage, and it feels slippery because it can break apart certain biological structures, molecules in there. But anyway, going back to this here, if we go beyond 14, the concentration of base is getting higher and higher. If we go below 0, the concentration of mass is getting higher and higher. So beyond these range, this limit here, 0 and 14, if we go outside that range, we go to higher concentrations. At higher concentrations, we have to start worrying about what? So did you guys have a chance to review that section at the end of chapter 14? Electrolytes? It's like 3 paragraphs long. So can you tell me where the ideal gas law works best? Under what conditions? Will you? Opposite. Higher temperatures and lower pressures. If we're at higher pressures and lower temperatures, our calculation is not going to be as accurate. So let me show you. Something. Do you know where all these pH equations work best? At higher concentrations or at lower concentrations? Where do solutions behave more ideally? Do solutions behave more ideally at lower concentrations, or do solutions behave more ideally at higher concentrations? Okay, finally got rid of that window. So you should read these 3 paragraphs. It's not even the whole section. You don't have to read the whole section. Excuse me, 14.9, solutions of electrolytes. Skip that, and then read interionic attractions. 1, 2, 3 short paragraphs. And then if you can explain figure 1424, can somebody explain figure 1424 for me? What's going on there?
Effective concentration.
Yeah. And if somebody can explain table 14.4 here, if you can explain what's going on here, then you understand those 3 paragraphs. If you can't explain it, then reread those 3 paragraphs or look in Wikipedia or do something to try to figure it out. There's something called the ideal. This is the ideal concentration here. The ideal concentration note is 3. These are the effective concentrations over here. You see that? So the ideal concentration is 3 molal. The real concentration is 1.31 molal. What happened? And so what happened is, how do you know? How do you know what the effective concentration is going to be? We don't know what it is going to be because we're not going to calculate it. You know, what's another name for effective concentration? Another name for effective concentration is the activity. And so activity is very important in chapter 13. So you should at least know what the activity is. And so the situation is the same thing happens here. If the concentration gets too big, then we shouldn't be using these ideal concentrations, the stoichiometric concentration. We should be using the effective concentration. Instead, what we should be doing is replacing all these concentrations with activity. But we're not going to do that. Instead, we're going to try to limit our calculations between 0 and 14, where it seems to work okay. If we go beyond 14 and below 0, then we probably shouldn't be using these equations. We should be using the exact same equations except with activities instead of the ideal concentration. But even when the concentration is low, there's still potential error there because of that. But anyway, this is the range, the typical range, 0 to 14 is what people say. The lowest pH measured for natural water is actually in California. I think the lowest pH was a -2 point something. And it happened to be in a mine pit, I think. And so there's a lot of waste, mining waste in there.
Maybe like super acid.
Yeah. Extremely acidic. All right, let's move on to ammonium chloride. I think this was also 0.1 molar. Chloride's neutral, and so we're just looking at ammonium. Ammonium's a weak acid, and weak acids hydrolyze water to form what? Or acids in general hydrolyze water to form hydronium. So we're going to form hydronium, and what's the other product of this? Ammonia. So ammonia is the conjugate base. So here's our acid ammonium, the conjugate base is ammonia. Here's our base water, the conjugate acid is hydronium. This is favored in the reverse because we're going from weaker acid ammonium to stronger acid hydronium. But what we want to do is we want to figure out how much reaction we have here. So what we're going to do is we're going to measure the pH. What did you guys get for the pH for this? 5.36. Okay, that's what we expect. It's a weak acid. So pH of 5.36 is weakly to moderately acidic. So what we have here is we have 0.1 molar. H2O is a pure liquid, and 0 molar and 0 molar. So essentially we reset it. So we're just starting off initially with all ammonium, and then we let it react. Minus X molar, plus X molar, plus X molar. And so what we're going to do is we're going to calculate Ka from this. Ka, we're going to need the hydronium ion concentration at equilibrium. Well, that's easy, because from the pH we can get the concentration of hydronium at equilibrium. The concentration of hydronium at equilibrium is just going to equal 10 to the minus 5.36 molar. Let's see what that comes out to. .365 times 10 to the minus 6 molar. Okay, we can plug that in here. Times the ammonia concentration at equilibrium divided by the ammonium concentration at equilibrium. And so the hydrogen we got from the pH, that's 4.365 times 10 to the minus 6. The ammonia will be the same. They're formed in a 1-to-1 mole ratio. We started off with 0 and 0. So this will be 4.365 times 10 to the minus 6 molar. And then over here, we're going to have 0.1 minus, I'm going to put this in decimal form. So I'll need 0.1, 2, 3, 4, 5 zeros, and 1, 4, 3, 6, 5. So this will be 0.09. That doesn't seem to be working. 0.099995 635. All right, then we can calculate our K. A value is this times that, so this squared divided by that. Does somebody have it? All right, this is our experimental Ka. Now let's look for the accepted Ka value. It's not found in Appendix D. So should we go out and buy another book? Maybe other books might have it. But we don't have to because we know that Ka for ammonium must equal Kw divided by Kb for what? Ammonia. And it turns out that, earlier I was saying there's an acid table and we don't need the base table. This is redundant. But our book decided to make a base table, and in the base table they put ammonia. And so we can go ahead and use that. So we have 1.0 times 10 to the minus 14, that's Kw. Now Kb, we look it up in the book, it's 1.8 times 10 to the minus 5. And so this gives us a Ka of 5.55 times 10 to the minus 10. So it seems like this is the same as acetic acid acetate. But If we go out to 3 sig figs for the K value, it's different. It's off a bit.
That for 1.9, I got 1.9 times 10 to the negative 11.
Times 10 to the negative 11. How about others? You got to the negative 10. Let's go ahead and double check it.
Yeah.
Well, take a look at the calculations again. This one we'll just say slightly off. It looks okay.
Oh, no, I was able to get that. I got the 0.
Okay, great. All right, so I'd like you to do this using the accepted Ka value of 5.55 times 10 to the minus 10. Calculate the pH expected. Okay, what we're going to do here is we're going to start the lab. We'll finish up the calculations tomorrow in lecture. For the lab, we're going to need the pH meters again. What I did was I took the hydrolysis of salts and buffer and then broke it up into two separate labs. So on Tuesday, we did the first part of the lab. Today, we're going to do the second part, but I don't really like the second part procedure, so I'm going to totally change it. And just the observations only. Yeah, just write down what you did. I'm going to tell you what to do.
No procedure, though?
No, you don't need a procedure. If your observations are thorough enough, then we're okay. All right, so if you want to work alone, that's fine. I think we have enough pH meters. But the first thing we need to do is we need to get the pH meter. Do you think the calibration's still good from Tuesday? No, we have to recalibrate it, unfortunately. But we have buffer solution back over there. And so grab the pH meter, calibrate it, and then we'll start.
If you have the cap on it, still like a cover on it,
I did, yeah.
maybe take that off, let it evaporate. If you want, when you check the I'll just do like half my. Now, where's dissolving that?
I mean, yeah, they're not disappeared. Just to gel all day. Don't make out. Yeah.
Why do you not go that?
You're scared?
meters. Prepare the function.
Yeah, you're going to prepare the buffer. Okay, once you calibrate your pH meter, grab a 150 milliliter beaker and get 50 milliliters of 3 molar acetic acid.
Do we read it?
Yeah, you're going to take a measurement of the 3 molar acetic acid and then just leave the probe in there. Okay, after you have that, or before you get it, get about 6 grams of sodium acetate trihydrate from the back bench. What you'll want to do is you'll want to get a piece of weighing paper like this and then fold it in half and fold it in half again to form quarters like this, and then weigh some sodium acetate in here, about 6 grams, a little less than 6 grams probably should do it. No, don't add any yet. Before you add it, predict what's going to happen in the reaction between acetic acid and sodium acetate.
How much of the acetic acid do you get?
50 milliliters. 50 milliliters of acetic acid. Yeah. Yeah. Yeah, we'll need the pH of the acetic acid. You're also going to need some 6 molar HCl and some 6 molar sodium hydroxide, about 10 milliliters each. In addition to that, you'll need 2 plastic pipettes. The plastic pipettes are near the weighing paper. One for the sodium hydroxide, one for the HCl. So 6 molar HCl, 6 molar sodium hydroxide, about 10 milliliters. It doesn't have to be exact.
What concentration?
6 molar.
Okay, 6 molar.
Yeah, both.
Okay.
HCl and NaOH, 6 molar.
I was trying to keep from the chair.
All right, so this is what you should have. You should have 50 milliliters of 3 molar acetic acid in a 150 milliliter beaker. 2 small beakers, one with 10 milliliters of sodium hydroxide, the other with 10 milliliters of hydrochloric acid, both at 6 molar. Six. 2 plastic pipettes, one for the HCl, one for the sodium hydroxide. And then measure the pH of your 6 molar acetic acid, or 3 molar acetic acid. Measure the pH of that. And then leave the probe in there. We want to get a stable reading.
Yeah. 6 grams.
You had 6 grams of solid sodium acetate trihydrate, but don't add it yet. So does everybody have the equipment? All right, the first thing is, can you predict the products for this reaction? Acetic acid plus sodium acetate? What are the products? This is double replacement. The products for this, it's a double replacement reaction, so we just swap the anions. So we're going to form acetic acid and sodium acetate. There's no change, so we say NR, no reaction. All right, that's no reaction for double replacement, metathesis. Then we check acid base. Well, it's the same thing. If you donate the proton acceptor, proton donor, same thing. And then finally, there's no redox here. So there's no reaction. You know what we're going to get? We're not going to get a reaction. We're going to get a stable mixture that contains both an acid and a base. That's a buffer. When we have a stable mixture that contains both an acid and a base, we call that a buffer. And so we're going to make a buffer solution, and this is our homemade buffer. So what's the starting pH? The starting pH is, what is the pH of your acetic acid solution? It's like 2, roughly? 2.8? 1.8? 1.9? Okay, that's acid. Acids hydrolyze water to produce what? Acids hydrolyze water to produce hydronium. Now we're going to add some base. Bases hydrolyze water to produce hydroxide. So the hydroxide is going to pull the pH up. So what you want to do is you want to add the sodium acetate slowly. We're going to add the sodium acetate slowly until you get to about pH 4 and then stop. And so what we're going to do is we're going to make a homemade pH 4 buffer. And the way we're going to make it is just keep adding the base until the pH gets up to 4 and then stop, and then the pH should be stable. So you're going to have to add it with stirring to make sure the sodium acetate completely dissolves. Yeah. If you overshoot 4, you can bring it back down by adding more acetic acid.